Hello all. In today's session, let we learn about a topic conversion of flip-flop in your unit 4. So, how to convert the flip-flops from one flip-flop to other flip-flop as we discussed the four types of flip-flops. So total conversions if you have four flip-flops is 12 conversions like SR to JK, SR to D, SR to T. So each flip-flop if you wanted to convert into other flip-flops, I will have here for each category 3 conversions. So total 12 conversions are available here. So in your conversions of flip-flops. So how to convert your given flip-flops of one flip-flop into your required flip-flop is using some procedure. So now in that procedure there are some steps are included. First we have to identify what will be the actual flip-flop and your required flip-flop. Thereafter, after identifying those required and your actual flip-flop, we need to draw the conversion table. In that conversion table, let me first write your state table of your required flip-flop, and upon writing that state table of your required flip-flop based on your excitation transition, so based on your state transition from present state to your next state, so we have to find your excitation inputs. So now for example, now if my flip-flop is your SR actual and your required flip-flop is your JK. So we have to draw your JK flip-flop state table. Thereafter writing that JK flip-flop state table. So we need to write. So here we need to draw the state table on your JK flip-flop, and then we need to find your excitation inputs which are required on your SR. So like that, so draw the conversion table. Upon writing that conversion table, we have to write your each excitation table in terms of a standard SOP as a function of your required flip-flop inputs and its present state. Thereafter, writing your SSOP expression, you have to minimize your each excitation inputs functions using your K-map method. And after finding that minimal expression, we have to draw the logical diagram which can convert your actual flip-flop into your required flip-flop. You have to transfer the required flip-flop inputs through that combinational circuits or your obtained minimal expression whatever you have. So that must be implemented using this combinational circuit, and combinational circuit output is fed back as your input to the your given or your actual flip-flop, and the output which is obtained from the actual flip-flop is your required flip-flop. So these are the required flip-flop inputs must be transmitted through your combinational circuit, and the combinational circuit output is coupled as your input to the actual flip-flop. Now upon transferring your required flip-flop inputs through combinational circuit and the outputs of combinational circuit as your actual flip-flop, it will give you the required flip-flop outputs. So this is the procedure which we follow for converting one flip-flop to the other flip-flop. So now let me take an example of SR to JK. So now SR flip-flop is your actual flip-flop and your JK flip-flop is your required flip-flop. Now we are going to draw the conversion table. In that conversion table, first let me write your the state table of your required flip-flop. So required flip-flop is JK. So we have mentioned the JK flip-flop state table. So upon writing that state table, then we will find your excitation inputs of your actual flip-flop which are SR. So now S and R is fine. We will find your or we will write the values of your SR. So based on your excitation input, so based on your state transition from present state to the next state. So these are excitation inputs. SR are your excitation inputs. So now these excitation inputs now depends on your state transition value. So 0 to 0, SR inputs are 0, don't care. 1 to 1, don't care. 0, 0 to 0, 0, don't care. 1 to 0 is 0, don't, 0, 1. 0, 1 is 1, 0. 1 to 1 is don't care 0. 0 to 1 is set input is 1. Reset input is 0. 1 to 0 is your S input is 0 and reset input is 1. So then we obtain your so which is the state is moved from your present state 1 to 0. So upon writing this, so here after drawing this table, so next we have to write your SSOP expression, which is a function of your JK, your required flip-flop inputs, present inputs, and your present state as a function of JK QL. So you have your functional value of 1 are the minterms for the combination of a 4 as well as for the 6. So minterm 4, minterm 6 are 1s, and the remaining minterms are having 0s and don't care. So we need to include your don't cares too. Don't care values we obtained for 1 as well as for 5. So hence we have mentioned here sigma d of 1 5. So which is S of jk qn is equal to sigma m of 4 comma 6 plus sigma d of 1 comma 5. In the same manner, for R input also we find your minterms. The minterm values for 3 is 1 as well as 7 is 1. So we included that minterms as sigma minterm. Sum of minterms are 3 comma 7 plus 2 don't cares are available on your 0 and 2. So plus we included that don't case also in the function of your R. So sigma d of 0 comma 3. So now 0 comma 2 are your don't case. So now so mapping your function using a 3 variable k map, j, k, q and are the input variables. So in order to derive your minimal expression, so we map your functions. So after mapping your function, then we'll go for the minimization technique by just grouping your minterms. So only 2 minterms are available. So we can form a pair. So hence here we can have your pair. So now this pair can give you the minimal expression which is j, q and bar. So row wise for this 2 minterm j is common and column wise 0 is common where q 0 is assigned on qn. So qn is represented in the product term as complemented terms. So qn bar. So next R is sigma m of 3 comma 7 0 comma 2. So hence here 0 comma 2 is the don't case and 3 comma 7. So only the possibility is the pairing 3 and 7. So after performing the possibility of pair, so we can have your minimal expression of R is equal to KQN. So now, so observing your each excitation inputs S and R here. So S value is JQN bar where R value is equal to KQN. So both product terms we have on your S and R inputs. Now the combination circuit is having your two AND gates. Now we were transferring your external inputs, JK inputs. So these two AND gates which are having here, one of the input is transferred from your present state complemented with the other input of your K is connected from your present state of Q. So upon giving the clock, so this actual SR flip-flop now with this connection of your AND gates, output of AND gates which are your combination circuit outputs are being transferred as your actual flip-flop inputs. Now this can function like a JK flip-flop. The same manner, so we can also convert your SR to D flip-flop. So here the required flip-flop is D flip-flop and your actual flip-flop, the required flip-flop is D flip-flop, actual flip-flop is your SR flip-flop. Now first we have to draw in your conversion table the D flip-flop state table. So as here D flip-flop is having only one input, so D in your present state and your next state we have indicated as a state table 0. So Qn plus 1 is equal to D. So hence, so here D whatever the D value is there, that will be your Qn plus 1. Next, based on your state transition 0 to 0, SR inputs are 0, don't care, 1 to 0 as it is resetted. So reset input is 1, set input is 0. So Qn is 0, next state is 1, set input must be 1 and reset input is 0. 1 to 1, no, there is no change in the state. So here S input is don't care and R input is 0. Now based on this, so we note that SSOP expression as a function of your two input variables, the required input and your present state dqn is equal to sigma m of 2 plus sigma d of 3. Next R is equal to sigma m of 1 as well as your sigma m d of 0. So now upon drawing that K map and you're mapping your functional value, so we could have that minimal expression for S is equal to D as this one is paired with your don't care. So then here it is S value is Boolean expression for S is equal to D where R is equal to D bar. So hence here we complement your D input is directly connected to the S input and upon complementing your D input, so output of your NOT gate if you are connected to the R, so then it behaves like a data flip-flop or the D flip-flop. The same manner, next example is JK flip-flop to D flip-flop. So required flip-flop is D flip-flop and your actual flip-flop is your JK flip-flop. So now we have drawn the T flip-flop state table. So 0, 0, 0, 1, 1, 0, 1, 1. So are the possibilities of your two inputs. So now if T is 0, your next state is 0, T is 0 and your present state is 1, next state is 1. So there is no change in the state. If T equal to 1, then we have your toggle state. So 0 is toggle to 1, 1 is toggle to 0. So this is the state table of your T flip-flop. Upon drawing this state table, then we could find your based on the state transition, we could find your JK1. 0 to 0 transition, JK excitation table is 0 don't care, 1 to 1 don't care 0, 0 to 1 1 don't care and 1 to 0 is don't care 1. Using your excitation table we can write this JK values. So upon writing this JK inputs, then we will going to write your standard SOP expression J, J in terms of T Q, Q of T or Qn. So which is only one minterm we have and two don't case. So one minterm is on your second, it is on minterm 2. So hence sigma m of 2 plus sigma d of 1 comma 3. So in the same manner, k only one minterm which is on 3 and 2 don't case 0 2. So upon using your two variable k map, so we can minimize the function. So in order to minimize these two functions, so we are using the don't case or considering those don't case as we are minterms. So t here t value. So here j is equal to t and k is also equal to t. So hence we have shorted your jk inputs and given to the common input terminal which is here t. So now it behaves. So upon connecting this, so shorting your jk inputs, so your actual flip flop is jk. So shorting your jk flip flop and given to the common input, now it behaves like a t flip flop. So now it is converted into t flip flop. So next t flip flop to d flip flop conversion. So here actual flip flop is t flip flop and your required flip flop is d flip flop. So now, so first we will draw the required flip flop conversion table D0, Q0. So next state is 0. So D0, Q is 1, present state is 1, next state is 0. So Qn plus 1 is as like your D. So hence we copied your D value on your Qn plus 1. So upon writing this, so based on your excitation or your state transition from 0 to 0 excitation table, we will write the values of your toggle input. 0 to 0, 0, 1 to 0 it is toggle, so T input is 1, 0 to 1 it is toggle, so T input is 1, 1 to 1 there is no change in the output, so or in excessive, so hence it is 0. So now T is written in terms of standard SOP as T is equal to upon marking a function it is equal to D bar Qt plus D Q bar Q D Qt bar or D Qn bar. So it is the exclusive OR of I can write it as Qt. So hence we have used a exclusive OR bit as a combination circuit. Combination circuit output is connected to the T. So output of your exclusive OR is connected as T input with a clock signal and the inputs for your exclusive OR is your Q of T as well as your T. Now it functions like a D flip flop. Your T flip flop now it is converted upon connecting this exclusive OR bit output as your toggle flip flop. So that it could function like a D flip flop. So like this you can convert your flip flops, one flip flop into the other flip flops. So this is our end of the session today. So next remaining conversions also you practice that. So all remaining 8 conversions practice it. So in the next session we are going to learn about your master slave JK flip flops.